Okay, only a minute late. Not bad. All right, so first off, I would like to say welcome to everybody. I know it's a little bit early in the morning, so I'm glad that you all decided to come out and learn something about cryptography. This session will be relatively high level. We're not going to get into a lot of theory. We're not going to get into a lot of math. We're going to focus on how you secure your data in real-world applications. Cryptography is extremely complicated, and there's a lot of ways that you can make mistakes that have substantial impact. So the goal of this talk is to give you the basics, give you the fundamentals, so that as you are implementing systems, as you're designing systems, you understand what to look for, you understand what you need to do the job right. So first off, a little bit about me. My name is Adam Caudill. I am a security consultant and researcher. Much of my job these days involves breaking applications. Everything from code review to penetration testing. Prior to that, I spent 20 years writing software for a living. I am one of those fortunate people that gets paid to do what I love. This is not only my hobby, it's my career. Securing systems is a constant battle, and one that begins with all of you. Developers are the key. Developers are the people that are making the decisions that matter when it comes to building secure systems. Many of the people I work with in the security industry stay trapped in an echo chamber. They never get out and talk to the people that matter. I make it a point every opportunity I get to speak directly to developers so that we can fix these problems before they ever happen. We can eliminate these issues before a hacker breaks in and starts stealing data and your company ends up, on CNN and everywhere else. That's why I'm here. And hopefully, through some of the stuff that we'll be talking about today, you can keep these type of events from happening. So, I'd like to ask a few questions about you. Who here regularly works with applications that use encryption? Excellent. How many people here regularly work on applications that don't use encryption but really should? Okay, that's about what I expected. Who knows what AES is? Okay. How about ECC? Good. If I talked about ECB, CBC, GCM, how many people in this room would understand what I'm talking about? Better than last time. I'm happy. So, you all know what cryptography is, but let's talk about the concept for just a second. Cryptography is the art of hiding data. And I use the term art instead of science on purpose here. But it is the art of hiding data from those that don't need to see it, those that shouldn't see it. In many cases, the people you're hiding it from are attackers. In some cases, such as around, say, password hashing, it's also hiding it from you. You should never be able to see your users' passwords. If you can, there's a mistake and you should correct it. Now, it's important to understand, while we're at this, what cryptography isn't. The first line there is really important. I have seen many people make that mistake. We just add encryption to this, and it's going to be secure, and everything's going to be great. One of the best quotes I've come across talking about encryption is that encryption is often the vault door on a tent. It is this incredible, unbreakable thing that will survive the heat death of the universe. Except for the fact that if I get access to your server, I can just grab the keys and decrypt everything and we're done. That's happened many, many, many times. So, while encryption is this incredibly powerful tool that is extremely useful, it's important to understand what it isn't. It doesn't make everything better. And I can tell you, as somebody that focuses on practical applied cryptography, that last line is very, very true. It does not make your life easier. And while we're using the term crypto, something else that it's not is cryptocurrencies. Yes, they are based on cryptography. They use it extensively. Interestingly enough, if you look at something like Bitcoin, the core protocols that it uses are the same things that are used in business applications today. It's just a different application of the same ideas, the same constructs. There is currently a fight going on between the cryptocurrency community and the cryptography community about the proper use of the word crypto. So at this point, if I don't include this slide, I would be driven out of the community. So, a couple notes on the talk itself. This is technology agnostic. This does not apply to any specific language, any specific framework. This can be applied everywhere. This is about applied cryptography in real-world scenarios, not the theory behind it, not the math behind it. If you start going into theory, it's easy to get lost in the weeds when it comes to crypto, because it really is an extremely complicated topic. And when you start looking at the interaction of different algorithms and building more complex systems, it's really, really easy to get overwhelmed. So we're going to try to keep things relatively straightforward here. There's a number of different things we're going to talk about today. Some of these we will go through in a fair bit of detail. Some of these we'll go through relatively quickly. Priority will be on covering the things that you're most likely to run into in, like I said, real-world scenarios. We're going to start off by talking about hashing. Hashing is a topic that surprisingly few people understand, given its critical role in essentially every crypto system ever created. A hash function is a one-way function, which just simply means there is no efficient way to take the output and learn the input. And by efficient, I mean anything less than a straight brute force. If a hash function is cryptographically secure, there is no quicker way of getting that data back. Some hash functions have been broken, which has led to quicker recovery or other interesting things such as collisions. There are various hashing functions that if you're using them today, you should stop. You should definitely not be using them in anything new. How broken these algorithms are varies. MD2, MD4, that's used for practice challenges these days. SHA-1, you have the ability to create collisions, but doing so is expensive. And by expensive, I mean, so far the only people that have been able to afford to do it is Google. Here's what you should be using. SHA-2 was created by the NSA to correct the issues with SHA-1 after they learned that it had flaws. SHA-3 was created by a public competition ran by NIST to create an entirely new hashing algorithm. Blake 2 is based on one of the entries for that competition. It is actually the best studied of everything that was submitted for SHA-3. With the upside, it's also the fastest. Blake 2 gives you the speed of MD5 with the security of SHA-3. Extremely high speed, extremely flexible. Hashing plays a key role in everything from digital signatures, file verification, MACs, which we will talk about later. This construct is used everywhere. So while it's something that's often glossed over, it's important to understand at least what you're looking at when it comes to hashing. Now, all these functions I've talked about so far are extremely fast. Even the slowest of these is phenomenally quick, especially with small inputs. In the vast majority of cases, that is exactly what you want. You want hashing to be as fast as possible so you can perform your validation and move on. Except one specific case. Password hashing is different. It is special. The reason for that is human beings are incredibly poor sources of entropy. No matter how good you think you are at coming up with random passwords, you're not. To make it worse, humans are even less able to remember entropy. You may be able to come up with a random password that isn't terrible. The odds of you remembering it is next to zero. Because of that, password hashing has to be handled a little bit differently. So, how many people in this room deal with systems that store user passwords? How many of you are hashing passwords with something like MD5, SHA-1, SHA-256? A number of people raised their hand just high enough to see it, and one person was brave enough to actually let the rest of the room see it. It happens. There's legacy systems out there. Those systems, though, like everything else, should be updated to use one of these. If you're going to interrupt a talk, that's the way to do it. So, today, if you're building a system, you would want to use Argon 2 as your password hashing algorithm. It is the best option available today. Your minimum option is PBKDF2. You should never, ever be using a straight hashing function. I don't care if you salt it or not. You should never be using a standard hashing function with passwords. PBKDF2 is almost at the point of being dropped from this list. It is barely making the line for minimum. The reason it's still there is the fact that it is implemented everywhere. There is not a language or framework that doesn't have it in place. Argon 2 is the hardest one to find because it is relatively new. Argon 2 was created as a result of a public competition to create a new gold standard in password hashing. It is the best option that's available today. These functions are all what are known as KDFs, or key derivation functions. With the exception of PBKDF2, they allow you to adjust the memory hardness and processing hardness, which means that you can increase or decrease the amount of memory necessary to compute the hash. You can increase and decrease the amount of processor time necessary to compute the hash. The goal is to find a configuration for your servers that takes as long as possible without causing a negative impact. This is the one case, the one scenario in cryptography where we try to make things as slow as we can. And here's why. If you are hashing your passwords with MD5, only the best passwords stand any chance. This is stats from a single GPU cracking system. One GPU. Make a point to look at the side of the slide there. That's in millions per second. Protecting a user's password can be a tricky thing to do, though, because it's a balancing act. You are balancing between server resources. The higher you turn up your KDF, your password hashing algorithm, the greater the risk of attack. Because there is the possibility of a denial of service attack by hashing lots and lots of passwords very quickly. But you are also trying to protect against the risk of, if those hashes are lost, an attacker being able to get them. Now, some people take password cracking seriously. That box was built by a friend of mine. That's 8 GPUs, top of the line. The stats from that box are just ridiculous. It's incredible. His customers, who most of which prefer not to be named, often buy more than one of those. They cluster those. 5, 10. The biggest one I'm aware of is 50 of those in a single cluster. Virtually nothing can stand up if it's poorly hashed. So if you have an attacker that's determined, if you have an attacker that is able to grab your hashes, be it SQL injection or be it court order from a oppressive regime, they'll get the passwords. Now we move on to secret key encryption or symmetric encryption. This is your data at rest. This is your data in a database. This is your data over the wire in hybrid crypto systems. There are two major types of encryption systems used, and they are based on how the key is handled. Public key, secret key, asymmetric and symmetric. Symmetric encryption is high speed, uses the same key for both operations, which means that there is the issue of providing the key to the person that's supposed to be decrypting it, be that somebody else or yourself in the future. Secret key encryption comes in two major flavors: block ciphers and stream ciphers. Stream ciphers are conceptually very simple. It basically breaks down to a secure random number generator. You produce an output the same size as your data. You XOR those two things together and you're done. Very clean, very simple, very fast. Block ciphers are substantially more complicated. And a big part of the reason that they're complicated is they can only encrypt up to the block size. AES can only encrypt 16 bytes of data. I am sure any of you that have worked with AES realize you can encrypt more than that. The reason for that is block modes. These are higher level constructs that sit on top of the encryption algorithm to allow you to encrypt more data at one time. But each one is different. Each one has upsides and downsides, which we will get to in just a minute. Some encryption algorithms are broken. Some of them are weak. RC4 is broken, and it's broken in a pretty amusing way. It's a stream cipher, which, as I said, is basically just a secure random number generator. The problem is it has biases. Certain positions are more likely to have a certain value. This has been known for years. The problem is those biases go far deeper and are far more significant than was originally understood. But it still took years to finally kill off RC4. The reason for that, and this is interesting, the reason for that is it is extremely fast. It is one of the fastest encryption algorithms that's ever been devised. Next, it's extremely simple. Back in the days where fitting something in a tweet was actually a challenge, you could actually fit the RC4 algorithm in one tweet. Now that we've got 280 characters, it's not fun anymore. DES has the issue of small key size. Key size is only 64 bits. At this point, that's trivial to break. So what you should be using is AES for block cipher, or Salsa 20, Cha-Cha 20 for a stream cipher. When using AES, you should be using, if at all possible, 256-bit keys. You do have the option of using 128. At this point, 128 is considered secure, although the guidance from NSA is that we should be moving away from 128 because of what may happen in the future, and we will talk about that towards the end of the talk. Now, like I mentioned a minute ago, cipher modes. These are higher level constructs that allow you to encrypt more than the block size. Bad comes in two classes. ECB is bad in a very, very special way. It actually reveals the structure of the data. It doesn't reveal the data itself, but it makes it clear what the structure of the data is. So, for example, if you have an image, a bitmap, that's encrypted, you can actually see the outline, the major groups, the color blocks, even though it's encrypted. ECB encrypts 16 bytes at a time, and nothing is carried forward. Nothing is done to prevent that structure from coming through. ECB should never be used. Period. End of story. If you have a system that is using ECB as quickly as you possibly can, get away from it. Now, if you're using AES today, there is probably a 70% chance that you're doing it in CBC mode. It is the most common block mode used. There is a problem, though, with CBC. CBC is not authenticated. There's nothing in there to tell you if the data has been altered. CBC just happens to have a really fun property. It's malleable. I can flip bits in an encrypted bit of data in the ciphertext itself. And when you go to decrypt it, it will still decrypt just fine, even though I've made changes to it. With some experimentation, you can get to the point that without ever knowing the key, you can control what it's decrypted to. The classic example of that is performing a transfer at a bank. You're moving money from one account to the next. Because it's malleable, I can do fun things like, say, change the amount that's being transferred. The message goes through, it decrypts fine, everything looks normal. CBC without authentication, if it is ever exposed to a potential attacker, is actually quite dangerous. And like I said, if you're using AES today, there's probably roughly 70% chance that CBC is what you're using. Authenticated encryption solves that problem. It allows you to ensure that the data isn't altered, that it is exactly what it's supposed to be. You can expose authenticated encryption to an attacker, and they're not going to learn anything from it. It can be authenticated in a couple different ways. One option is to use a mode such as GCM, CCM, something like that. These are modes that have authentication baked into them. They automatically produce an authentication tag so that when you perform the decryption step, that tag is validated and you only get your output data if the tag matches what it's supposed to be. Your other option is to use a MAC, or a message authentication code. If you're using CBC, this is one of the more common ways of using it safely. So what you would do is you would, with a separate key, generate a MAC for your ciphertext and use that to validate that it really hasn't been altered. And we'll talk more about MACs coming up shortly. All right, moving on to public key encryption. This is an area of encryption that it's almost magical, the way it works. The concept is something that is absolutely beautiful. It allows me to send you a message in such a way that anybody that monitors everything that we communicate to never learn the contents of. It is the reason things like TLS work. It's the reason things like PGP work. It has one major downside, and that is it's slow. It is actually, compared to symmetric encryption, really slow. It is, as I mentioned, absolutely vital to the use of TLS. Pretty much all modern communications protocols use public key encryption in some way, shape, or form. Public key encryption dates back to the 1970s when RSA was invented. It was actually invented slightly before that by GCHQ, but they kept it classified and it was independently rediscovered a couple years later. RSA should not be used today. That is unfortunate for some, that is painful for some, but the fact is, it should not be used today. RSA is incredibly slow. It is extremely error-prone. Old vulnerabilities keep coming back. There is a new vulnerability, against TLS that was announced just a few weeks ago, called Robot. Robot is based on a vulnerability that was found 19 years ago. The only change in Robot compared to the original was that they came up with a more efficient way of detecting it. That's it. It is the exact same vulnerability. 2 decades old. Still biting people today. There are ways of implementing RSA securely, but that doesn't change the fact that the vast majority of libraries, the vast majority of code that's out there, doesn't use these techniques. It is more luck than anything that has kept people safe over these years. The other thing to avoid is the world has steadily moved towards ECC, or elliptic curve cryptography. Just a quick bit of background on those two. ECC and RSA are based on different, very, very hard math problems. And their security is based on the assumption that those problems are actually hard. The minute that one of those problems is found to not actually be hard, the security of the system is gone. The problem ECC is based on is believed to be harder than the problem RSA is based on. The problem, though, is ECC is, based on a series of curves. Those curves can be produced in a number of different ways. Curves can have interesting properties that may or may not be documented. It is possible for me to create a curve that you could perform your encryption against that actually has a backdoor to it. So it's important that when you're evaluating ECC libraries, when you're evaluating algorithms, that you understand the origin of the curve that you're using. I know that is terribly confusing. The key point there is just don't blindly trust stuff. Don't blindly assume that just because a library implements it, it's actually correct. What you should be using is one of these two, 25519 and 448. You will see them written in different ways depending on the context. For example, you will see ED448 or X448. Those are all relating to the underlying curves there. Those are the ones that you should be using. Those are well documented, well tested, and how the curve was discovered is very cleanly documented with clear explanations. There are a number of different libraries that implement this stuff. The most widely available is a library called libsodium. Who here has heard of libsodium? Decent number, good. Libsodium is actually written in C, so it has a C, standard C API, but has language bindings for essentially everything anybody has ever thought of. It is a opinionated library, which means it doesn't give you a lot of control because it was designed to do the right thing by default. If you're looking at algorithms, AES and GCM mode, salsa, ECC using these curves. Libsodium is probably your easiest option to use these. And the good thing is, because this is a library that is cross-platform for everything, essentially, with language bindings for essentially everything, it makes interoperability between systems extremely simple. Which, as development shifts more and more towards multi-stack environments, where it's no longer the monolithic designs that it once was, where there is one technology stack used for absolutely everything. The use of a library like Libsodium makes it so much simpler to build applications that can interact easily. One of the things that people have found over the years is that, for example, if you have a .NET application using its native crypto support, you have a Java application using Bouncy Castle. Try getting those two things to talk. It's fun. So, moving on, message authentication codes, MACs. A MAC is essentially a secret key signature. If both parties know the secret key, they can compute the MAC and validate that it matches what they expect it to be. This is, as I mentioned earlier, this is extremely important for things like authenticating block cipher modes. These functions are normally based on hashes. Now, one thing I will note, just so you understand, so we talked earlier about hash functions and which ones you should avoid. Functions like MD5 and SHA-1 that you really should not be using today. You will occasionally still see references to things like HMAC SHA-1, HMAC MD5. If you look at the definition of cipher suites in a TLS configuration, you'll see references to MD5 and SHA, which is a reference to SHA-1. These are used in a HMAC construction. HMAC only requires that the underlying hash function be a pseudo-random function. It doesn't have to be collision resistant. It just has to be a pseudo-random function. So if you are doing like signature validation, if you're doing file validation with SHA-1, you have a problem. If you're doing HMAC with SHA-1, you're fine. You don't need to worry about it. Because it relies on different properties from the hash function. So this is one of those areas where different pieces of the system interact in interesting ways. Because of the HMAC structure, because of that construction, it completely changes the security properties of the hash function. And this is something that is common, surprisingly common, when it comes time to design a crypto system. You will find that there is very interesting and often unexpected interaction between different algorithms. This is one of the reasons it's really important, if you're designing something that's of any real complexity, to make sure that you talk to somebody that actually knows cryptography, to make sure that you're not inadvertently introducing a combination that doesn't work, a combination that has side effects that aren't clear, that aren't obvious. This is something that somebody that's been working with this stuff for a long time can tell you at a glance. Everybody else, oh, that seems fine. It takes a lot of experience, a lot of knowledge to be able to look at this stuff and understand. Yes, sir. No, you don't. It is a extremely small community, and it is very specialized. There are a number of consulting firms that do this type of work. There are some developers that have focused on it, but it's not that many, which is really unfortunate. The good thing is those that do it generally want to help. They didn't get into this because it was a paycheck. They got into this because they have a passion for securing systems, because they have a passion for learning, because they have a passion for these technologies. If you would after the talk is over, I can actually point you in the direction of a couple of firms that specialize in this type of work. All right, moving on to something that I find just slightly more interesting. Signatures. This is fun. Signatures are based on public key cryptography. They conceptually share a lot with a MAC. They allow you to verify that data hasn't been altered. But what's important is they allow everybody to validate that the data hasn't been altered. To validate the signature, all you need is the person's public key. That's made freely available. So anybody can verify this. This is what makes TLS work. This is what allows CAs to function. This is the key bit. Now, like everything else in cryptography, there are good things and bad things. There are good algorithms and bad algorithms. DSA, ECDSA are a couple of the most common signature algorithms available. They are also absolutely horrible. Both of them share a very interesting property. They rely on a strong random number generator to produce their output. If the random number generator fails, you end up exposing your private key. The failure is as catastrophic as it could possibly be. This is the kind of algorithm that a person would design if they wanted you to make a mistake. And it has happened. Sony, for example, learned the hard way that this is a problem. The software signing key for the PlayStation 3 was leaked as a result of a bad random number generator. A substantial number of bitcoins have been stolen over the years because these algorithms and a bad random number generator. Somebody was able to compute the private key. Once they had the private key, they were able to send the bitcoins to themselves, and done. Over. Thankfully, there's a better option. You may recognize those numbers. Thankfully, that is also implemented in libsodium. You may notice a trend here. Performing signatures with ECDSA and DSA is tricky because of the requirement for a random number generator. EDDSA does not have that flaw. It was designed from the ground up to eliminate that problem. That is the biggest part of the reason why it even exists. The original designer of it was trying to fix that problem because it had become obvious just how dangerous those algorithms were. These algorithms are really useful for interesting applications. Obviously, like I mentioned, they're key for TLS and for, the keyless certificates. They are what makes Bitcoin work. It's how you're able to send and receive payments or value or whatever it is Bitcoin people think they have these days. It's useful in things like, say, for example, file validation. How do you know a file hasn't been altered? How do you know somebody hasn't changed something that they weren't supposed to? It's a construct that's not really understood to the level it should be, but is extremely useful. And the more you dig into it, the more use cases you find for it. All right, slightly off schedule, so speeding up just a bit here. Okay, key generation. This is the one that so often people get wrong. And it is so vital to everything in cryptography. I have performed reviews, either penetration tests, code reviews on countless applications. You would be amazed how often I come across something that boils down to that. It's not that bad in the code, but once you go through it, once you analyze what it actually does, you realize it really is that. One of the more common ways you get to that is the use of a bad random number generator, which can be, anything from PHP's mtrand, Java.NET, C's native random functionality. All of those are awful. And using a static seed, hard coding the seed value for the random number generator, which means that the output is fixed, which means it is that. It is a long, complicated way of that. Recently, I was asked to review a bit of ransomware. This specific ransomware would read in the first few kilobytes of a file, encrypt that section of it, and then replace it with random output. Well, this specific ransomware was actually written in PHP for some reason I don't understand. Yes, they actually shipped ransomware targeting Windows. So it was the PHP file and the PHP binary. I don't know. Anyhow, they were using PHP's mtrand to create the output. Well, it just so happened that they also used the same instance of mtrand, to create the encryption key. mtrand has a 32-bit seed. If I can brute force that seed, I can predict everything it is ever going to produce from now to the end of time. And they were so nice to have written that random data to the beginning of the file first. So all I had to do was find the first file that they encrypted, look at the first few bytes in that file, brute force the seed until I came up with that same output, and then done. I've recovered the encryption keys, I can decrypt everything and put it right back where it was. The whole process just takes a few minutes. If they had used a proper random number generator, the data would be secure, and the only way to get back the data would have been to pay the ransom. The use of a bad random number generator completely broke their attempt at stealing money. So we're in a very interesting time in cryptography. Typically, this is a community that moves at glacial timescales. Things don't go fast. Things aren't exciting. When things get exciting in cryptography, it's typically bad. This is one of those areas you don't want exciting. You want boring. We have recently been making good progress at killing off some of these old dangerous algorithms, moving on to things that have been more proven to be safe. But at the same time, we are preparing for something else, something bigger, something exciting. What you're looking at is a 50-qubit quantum computer produced by IBM. If this thing actually works, it will achieve quantum supremacy. This is the most disruptive change to occur in cryptography since the invention of the general purpose computer. And I don't say that lightly. This changes everything. The reason that NSA has recommended the move away from AES 128 is this thing. They don't believe that 128-bit keys are going to be secure. The reason that RSA is increasingly being deprecated is this thing. If Shor's algorithm, a quantum algorithm, actually proves to be as efficient as it's believed it may be, it will absolutely destroy the security of RSA overnight. Everything protected by RSA today is at risk if these things actually work as well as some people are predicting. The risk at this point is not entirely clear. We are essentially at the stage of the very first integrated circuits when it comes to quantum computers. They're unstable. The output often resembles a random number generator instead of a computer. They are enormously expensive. The engineering is incredibly complicated. Nobody knows when the first general purpose quantum computer is actually going to be functional. Could be a year, could be 2, could be 5, could be 15. Once it hits, cryptography changes. The algorithms you use today will largely have to be replaced. There is a competition going on today, ran by NIST, to find new algorithms that are safe in a post-quantum world. That has also been exciting. The algorithms are falling like dominoes. One after the next is being broken. In one specific case, it was actually found that it was more efficient to break the algorithm than to use it properly. Things are exciting. Exciting isn't good. If you would like to do some more research, if you'd like to do some more reading, there are a couple books I highly recommend. The first one is Serious Cryptography. This is currently the best book available on the market. If you don't have a copy, you need a copy. The next one is Cryptography Engineering, another excellent book. It is... This isn't the one I would start with. There's a lot of really good information, but there's a lot of context that you need to understand before you read it, because otherwise you'll make bad decisions. Yeah, I highly recommend it. The author is absolutely brilliant. It is worth every penny. Right, and with that, everybody, thank you so much. I appreciate your time. I hope you learned something.